I'm going to be talking about the status of this field, which is to say our understanding of how gamma rays are produced in gamma ray bursts. And we don't really have. So let me just say at the beginning, we don't really understand how gamma rays are produced. And so this is more in the terms of telling you various ideas, where we stand, and hopefully to generate a good discussion. There are a number of people who are experts on this topic. And then there are also many other people who are not actively working on and thinking about this particular problem. So my hope is to generate a good discussion and to address how we can go about solving this particular problem. So that's my, my goal. The first maybe order of business is to say why we care. Why do we want to know how gamma rays are produced? We can do plenty good astrophysics and astronomy without knowing the emission mechanism, the radiation mechanism. So let me motivate why is it that we would care, or why would you care? And one of the reasons certainly from my point of view is the following, that gamma rays are produced at a distance which we can say very confidently is far away from the central engine. So there is an explosion taking place, there is a relativistic outflow. Those are well-established facts. And then the gamma rays are produced at some very large distance from the central engine, something on the order of, we don't know exactly what. I will say more about it a couple of slides down the road, but maybe something on the order of maybe 10 to the power 14 centimeter, 10 to the power 15 centimeter away from the central engine. And the source is completely, the central engine itself is completely opaque, completely hidden to our direct view. So the only way we can understand what's going on in the central engine is indirect, but it is as direct as it is going to get. And that is understand the radiation mechanism and then work our way backward to the central engine. So there is a motivation here, not just driven by the pure, by the only interest in trying to understand gamma rays for its own sake, but use that understanding to get back to the central engine physics. So that's the motivation. And this can be broken up, this particular process can be broken up into two parts. One is that we have this relativistic outflow, and that relativistic outflow, the energy in the relativistic outflow gets dissipated at some distance from the central engine. So there is a dissipation process, and then the energy that gets dissipated is converted into gamma ray. So these are two different processes, and I want to talk about them separately. So how the energy, for instance, from the gamma ray, from the relativistic jet is converted to thermal energy, or energy given to electrons and protons. Many proposals are there, but these are the main ones here. That if the jet, for instance, is baryonic jet, then there could be internal shocks converting the kinetic energy of the baryons to thermal energy, or it could be a Poynting jet, magnetic dominated jet, where the magnetic energy is dissipated and that energy is deposited into electrons and protons, and then radiated by wide variety of different processes have been proposed. These three are probably the main ones. It could be synchrotron, self-Compton or SSC, or it could be photohyspheric mechanism. These are the three, and I highlighted photohyspheric mechanism because a lot of work in the last, I would say, 4 or 5 years has been done on the photohyspheric mechanism, and there has been kind of a shift in thinking on the part of some people that maybe that's how gamma rays are produced. Again, this is by no means a complete list of people who have worked on this thing or papers. This is a very small subset of the papers written on this particular topic. Let me take up the first thing, and that is how the energy is dissipated. I would say the current paradigm continues to be this internal shock, and I'm going to not say much about it. In the next talk, you will hear more about the internal shock and its status of what it can do, what it cannot do. So I'm going to have you wait for the next talk to learn more about it. Only thing I would say, maybe it has already been pointed out, that internal shock, as the name suggests, are shocks within the outflow. So you have got slow, part of the moving jet and fast part of the moving jet. They come together, they collide, and in the collision, part of the kinetic energy gets converted to thermal energy. That's the basic idea, simple idea. And as I say, you will have to wait for the next talk to address the merits of it and the success of it. Let me turn to the radiation mechanism. There is a whole set of things that I could talk about in the, for a Poynting jet and its dissipation and so on, but I'm not. I'm just going to budget my time in a way to focus on things and get to the, how gamma rays are produced. So radiation mechanism. One thing that would help a great deal is if we have some way of figuring out the distance from the black hole or the neutron star that is produced in these explosions, the distance from that compact object where gamma rays are produced. If we could figure that out, then that would shed light as to what the mechanism may be. As an example, if for instance you find that gamma rays are produced at a distance which is much larger than the photospheric radius, then you know that it couldn't be the photospheric mechanism. It's something else. So that's the idea. And do we have some information as to the distance where gamma rays are produced? I would say we have some information, limited, for a limited number of bursts, but we do have some information. And I want to share that with you in this slide and the next. So we have some information to the distance from the central object where gamma rays, MeV, for instance, photons are produced. And one method is this, that very often, so what you're looking at here is the X-ray light curve. This is a burst, but it's a pretty typical burst. Detected, this one is detected by Swift, and you have got a very much of a excellent time coverage from prompt and subsequently, which was one of the big accomplishment of the Swift satellite. And what is seen very often, more than 50% of the cases of gamma ray burst, that if you look at the X-ray light curve, then after the prompt phase lasting for a few tenths of seconds, there is a very steep decline of the X-ray flux. Now, one possibility is to exploit this very steep decline. So the flux is declining as 1 over time cubed. And that cannot come from afterglow or external shock. One can rule it out with good deal of confidence. So which means that it is reflecting something about the central engine activity. And you can use this time over which this decline is taking place of the X-ray to get a handle on the distance from the compact object where gamma rays are produced. And the relationship for that is the distance is given by the variability time, in this case the time over which the X-ray light curve is declining, and times the speed of light and times the relativistic factor gamma squared. So using this, one can do this exercise for a number of bursts, and what you find is that the distance is something on the order of 10 to the power 16 centimeters. So that's one way of doing it, and that provides some answer. The other one is that we have a number of cases, a small number, but there are some cases where we see bright optical flash during the prompt phase. And the good thing with that is that that provides a completely different, independent way of making an estimate of the distance from the central engine where gamma rays are produced, and the optical, more particularly the optical is produced. And then of course there is the assumption made that optical is produced at the same place where gamma rays are produced, and that would be a reasonable thing to assume if the optical is correlated with gamma rays. And the way it comes about is that you can make a measurement of the distance from this is basically optical thickness argument. And so synchrotron self-absorption provides a limit to the distance, and that also turns out to be something on the order of 10 to the power 16 centimeter for a famous burst, the so-called the naked eye burst. And then this thing has been done for a number of other bursts with similar answer. So that's the second way of doing it. There's a third way of doing it, and that is make use of very high energy photons that are detected by Fermi LAT, and make use of that to determine what the Lorentz factor is using the pair opacity argument, and then use the Lorentz factor that is determined and the variability time of the MEV light curve to, again, it's the variability time and distance argument. Putting it together, one finds that the distance is once again of order 10 to the power 16 centimeter, provided that gamma is 1,000, which is what some people think that Fermi bursts are telling us. However, that is really, it is disputed. It may be if you have multi-zone models or more sophisticated calculations, the Lorentz factor may not be 1,000, but maybe 300. But even if it is 300, that tells you that the distance from the central engine where the gamma rays are produced is still large, 10 to the power 15 centimeter, much larger compared to the photospheric radius, which is 3 orders of magnitude smaller. So at least I would say the bottom line here is that there are a number of bursts for which there is a reasonable case to be made that gamma rays are produced at a large distance compared with the photospheric radius, and therefore the emission mechanism is not photospheric in origin. I should say, maybe as an aside, I should say that if the Lorentz factor were to be about 1,000, as some people suggest, then that is really approaching the limit of what you can obtain, or maybe even exceeding the limit of what you can obtain for a baryonic jet or a leptonic jet, which is associated with a thermal fireball. So you can pretty much, if you can really establish that gamma is 1,000 or more, you can rule out thermal fireball model for GRBs. So it's an important thing to really constrain as best as we can. So how is the MEV, how are the MEV photons produced? Generally, as I say, there are 3 main ideas and 3 main possibilities, and all of them have problems. So in the next 3-4 slides, I will mention these ideas, point out the problems with all of these ideas, and tell you way out, where I see a way out, okay? And then you decide as to what you think what might work. And then the remainder of the talk, where we are going, the remainder of talk will then focus on higher energy photons, GeV photons, where I think we do know at least a good part of this story. Not the full story, but a good part of the story. And that's what I would share with you. So MEV photon could be a synchrotron. And that's a straightforward possibility. And it's got strengths, it's got weaknesses. If it is synchrotron, then it has following immediate consequences, that the synchrotron frequency should be, which is related to the magnetic field strength, the Lorentz factor of electron squared, and the Lorentz factor of the jet should be order of hundreds of keV. That is what we see where the gamma ray emission peaks. Now, with that, one can calculate the cooling time of these electrons, and that's very, very short time scale. And so that leads to the following problem, that if electrons are cooling down on a time scale very, very short, look here, less than a microsecond, then electrons are in the fast cooling regime, and the spectrum that you should expect below the peak should be very soft, with the flux, specific flux decreasing as 1 over the square root of frequency, or alpha, the photon index of minus 1.5. That's a well-known problem. It was pointed out by numerous people in the past, going back to 15 years or so. So that's a well-known problem, and there are ways out of it. And ways out has been suggested that maybe you could have, for instance, the radiation produced at a very large distances where the magnetic field is weak, for instance, and that could more or less do the job of weak magnetic field. Therefore, electrons are not really cooling so fast. And if that were the case, it can work. And it was pointed out by, as I say, a number of people here. But it requires gamma rays to be produced at a distance greater than 10 to the power 16 centimeter, and the jet Lorentz factor to be greater than 300. And that the two together means that you can't have variability time of less than a few seconds. And that's the problem. It has other problems. It requires very high Lorentz factor for electron, and it's difficult to see how to produce it. Lorentz factor for the electron that you need is something on the order of 10,000 or more. That's difficult. It's been suggested, again by people here in this room, that maybe you could have two problems, two bad things leading to something good. You can have synchrotron cooling, but you couple it with inverse Compton cooling. So there are two bad things. But if inverse Compton cooling were to dominate and in the Klein-Dischner regime, then you could have this bad spectrum. This soft spectrum problem can be solved. And turns out that it does help, but not enough. Not enough to really solve this problem. The thing that seems to me like the most plausible thing, if one were to believe that it is a synchrotron process for the MEV, that it is electrons are being continuously accelerated. So as they are radiating and losing energy, they are also gaining energy by some process. And that could fix this problem of this low energy spectrum. Then there is SSC, or the synchrotron self-Compton. It is, has its own strengths and weaknesses. There are a number of weaknesses that I point out here. And they are, first of all, the synchrotron self-Compton process is very sensitive to the electron Lorentz factor. The synchrotron, as I showed on the previous slide, has a frequency which increases with electron Lorentz factor is squared. SSC, that photons are inverse Compton is scattered. So you pick up an additional factor of gamma electron is squared. So the dependence of where the peak will be for the SSC is gamma electron to the power 4. Now in that case, you should expect just a small variation in the electron Lorentz factor to give you very different peak frequencies, and therefore there should be a very broad distribution for E peak for observed gamma rays. Not so. It's fairly narrow. These are 4 different observatories, and they all find consistent result, and they are fairly narrow. So there is a problem here. The other problem is that it is easy to show that SSC requires some very special radius for energy to be converted to gamma rays, for the reason that the energy requirement going into electrons for the inverse Compton component, that requirement on energy in the electron increases as distance cubed, whereas the energy in the magnetic field for the synchrotron part is decreasing with 1 over distance to the power 4. And so the two together, there is a minimum. And if you go away from the minimum in either direction, shorter distance or larger distance, the energy requirement becomes huge. And therefore, there is a fairly narrow range of radius. Within a factor of a few, that is where the SSC should operate. And that's very difficult to see how nature could do that. And so that's another problem. The last problem is that if it is SSC, then you expect the synchrotron part to be very bright. To be able to produce the MEV photons that we see, it should have a bright optical. And the second order inverse Compton, which will give you energies, photons of energies of GeV and more, should also be there. And we have never seen a peak. Fermi has never seen a peak, second peak, in the GeV band. So that means that SSC is fairly tightly constrained. This is not to say that for every single burst you can rule out SSC. These are very general argument. If you take a typical Gordon variety burst, then SSC has got a problem of these kinds. Thermal part. This is something which is being considered, I would say, increasingly more in the last several years. And so I thought that I will at least give you a quick rundown on where we stand on the photospheric model. When people say photospheric model, it is really photospheric emission, but added to it something extra. That is, there is some dissipation of jet energy taking place below the photosphere, and that heats up the electron, and then electron inverse Compton radiation, either coming from the central engine or produced in situ, and so multiple inverse Compton taking place. So that's the idea. And this I have already mentioned, that there are a number of cases where it seems, with the caveats already pointed out, but it seems that gamma rays are produced at a radius much larger than the photospheric radius by 3 orders of magnitude or 4 orders of magnitude. So if that is correct, then you do not have 15. Then you cannot have photospheric emission. The other problem is that if it is really a photospheric emission, then the natural expectation is that you should have a hard spectrum below the peak should increase as nu or even nu squared, which is the Rayleigh-Jeans part, and that's really rare. It's not that we never see it, but it's fairly rare. And then there are theoretical considerations, and I have pointed out to a number of papers here. 2 recent papers I thought are certainly worth mentioning here, and that is that for a photospheric model to work, you need to dissipate the energy, whether it's kinetic energy or magnetic energy of the jet below the photosphere at a optical depth of 10, 20, 30, or 5, not much greater, not much less, to be able to then non-thermalize the photon energy and make it consistent with the observed spectrum. And that means a certain degree of fine-tuning, possibly certain degree of fine-tuning, is needed to be able to dissipate the jet energy at more or less the right optical depth and produce the spectrum.
Yeah, the point I was making in my talk is actually that yes, you need some dissipation both deep in the flow and also close to the photosphere, but it need not be localized. It can be a continuous.
It can be a continuous process.
Continuous. You convert some of, for example, kinetic energy to the internal form, but you can do it over and over again over a large range of radii in principle.
You could. But if you were, for instance, as an example, if you were to, for instance, produce energy at an optical depth of, say, 1,000, as an example, those photons that you're producing at an optical depth of 1,000, they get completely thermalized.
No. You can produce photons at these, but you can use the same photons later.
Yes.
To produce.
True. That you could do. You produce the photons at an optical depth of 1,000, and you
let them passively cool. After that, of course, you lose the energy.
Correct. And then you have to come back and inverse completely scatter these photons.
Yeah, but all this can be done and obtain the spectrum that you more or less see if you do it continuously.
I think you're addressing, there are 2 issues. One is how you generate the entropy. This can be done by dissipation, for example, dimension at small scales, or by injection. I think that the estimates of the R naught are, the original estimates are, give you a too small size. Secondly is the dissipation near the photosphere which produces the emission. If you just, for example, consider internal shocks with gamma of 1 to 100, you naturally get, by your argument, with something which is, let's say, 10 times the dynamical timescale of the engine, you get a dissipation at optical depth between 1 to 50, as you said. This is quite natural, it's not fine-tuning. And you're right, the issue of entropy is still there.
Yeah.
I don't think it's a major problem, but...
Let's look at a particular model. Look, I mean, so far it was very general. So I thought that I will share here one particular model and point out that there is some fine-tuning. If you look at individual model, then you can see the nuts and bolts, and you can see some fine-tuning going on. Although the proponents of the model would not say that there is a fine-tuning. But it appears to me, so for instance, there is a particular idea of this photoaspheric emission model, and that is based on neutron and proton. And the way it goes is this. Again, it's an audience consisting of people who know quite a lot about it, and then people who don't follow the subject closely. So this is for those people who don't follow the subject closely, is that you have got in this outflow protons and neutrons. They are coupled up to a certain radius, and then they decouple when there is too infrequent collision between the protons and neutrons. Then they decouple. And then what happens is that some larger distances, they may collide. And there are various ways of doing it. One particular possibility is, this is considered by Andrei Beloborodov, that you can have, for instance, decoupling taking place between the 2 during the acceleration phase, and then scattering after the decoupling. But that requires a very high Lorentz factor. The Lorentz factor should be something on the order of 485 or 500 or greater. Then you can have this decoupling taking place during the acceleration phase. The more possible or more plausible scenario is that you could have internal shock consisting of protons and neutrons, and in the shock, the protons get accelerated and deaccelerated, meaning slowed down, but the neutrons not. And then you have got now protons and neutrons with a differential velocity, and there would be some collision taking place between the two, and that converts the fraction of the kinetic energy to thermal energy and gets radiated away. So that's a fine idea, and it's an example of, for instance, a concrete example of the photospheretic emission. The only trouble is the following, that the radius where the internal collisions take place is given by the variability time of the jet luminosity, and that scales as gamma squared, whereas the probability of neutron-proton collisions drops like gamma minus 3. And so putting the two together, the radius of collision divided by the quote-unquote neutron-proton collision radius scales as a high power of gamma. So to make this thing work, you do want to have this thing take place not far away from this neutron-proton collision radius. Otherwise, too inefficient. Oh, is it 1 minute?
Small remark. No. Small remark. Within these distances inside the photosphere, you don't need the neutron proton collisions to create non-thermal spectrum, because the shock can give you the non-thermal spectrum just by scattering the photons themselves.
That's true. That's true, but you do want to convert. You're trying to convert a fraction of the kinetic energy.
It will convert
you have to
fraction just
exactly
because
right.
of the photons themselves scattering onto the
you could.
fluid coming from the outside.
You could do that. You could do that. But this particular model, what it is doing is that it is colliding. So I say it's very specific model. Yeah. Okay. So there are other ideas which Amir probably talked about on Monday, I guess, right? You must have talked about that. So look, this particular idea does require there to be collision between the neutrons and protons, and that does require this fine-tuning that gamma can't be outside of this range, otherwise the process is just too inefficient, okay? So there are problems with this thing. How am I doing? Probably not so good.
No, I will let you more time because most questions were asked during the talk. So.
Well, as I said, that was the best part of it. Anyway. Okay, right. So let's turn to this topic and high energy photons. By high energy photons, I mean photons with energy greater than about 100 MeV. And I would make a distinction between the photons, the high energy photons produced during the prompt phase, which means for long duration burst, something on the order of 10 seconds or 20 seconds. And then we do see these photons continue. We see these photons for time duration of closer to 1,000 seconds or 2,000 seconds. So I would like to make a distinction between the prompt phase and the quote-unquote afterglow phase. So, and there may be, because there may be two different mechanisms at work, possibly. And there are lots of ideas, again, suggested. It could be hydronic process, particularly during the prompt phase, which could be responsible for these GeV photons. Again, only a partial list. The trouble with the hydronic model is that it's very inefficient. You need a lot of energy in the jet to be able to produce GeV photons that Fermi sees. That's the main problem. It could be internal shock, for instance, or SSC, and again, you will have to wait for the next talk to hear more about it. Or it could be afterglow. And by that, I mean the same process that is producing X-rays and optical and the radio at late time. Those are the ideas. And this is basically tells you what may be at work. This is a very recent burst, April 27 of this year. And the beautiful thing about this burst is that you have got very good coverage in the GeV band, 2 to 100 GeV, about 1 GeV coming from Fermi LAT. Then you have got Swift band providing coverage in 15 to, in this case, 50 keV. Then Swift XRT providing coverage between 0.2 and 10 keV. These light curves, again, see these light curves are extending for the X-ray 100 days, for GeV several hours or more. Then there is optical and radio. All of this thing is there. And just notice, the similarity between the GeV, the X-ray, and the optical. They are exactly parallel to each other. So this really requires, I think, not much of an interpretation. Either it is a huge big coincidence that all of these things are coming from different process and yet have the same decay, same behavior. And I think that requires quite a bit of a stretch to say that you have got very different processes at work and giving the same behavior. It's possible that nature could be devious and fool us, but I think it's unlikely. So with this particular example, I wanted to show you that it seems that you have got the same underlying process for all of these things. And that is the afterglow. There is another example with the data not as rich as the previous case, but very nice data, similar case. So the basic idea is that you have got this jet which is moving outward and interacting with the surrounding medium, and then there is a synchrotron process that produces the X-ray, the optical, the radio, and also the GeV. That's the basic idea. And what I thought is that I will share with you a theorem, and it really is a theorem, simple, nice theorem, and that is that whenever you are looking at emission coming from a self-similar shock wave and by the synchrotron process, then the emission that we see, the flux, the specific flux that we see above the so-called synchrotron cooling frequency is completely independent of the density of the surrounding medium and has a very weak dependence on the magnetic field strength. Very, very weak. It may sound counterintuitive, and hence the proof that I have outlined, but I don't have time to go into the proof in detail. It's a very simple set of arguments, the bottom line being the following: that the flux from a self-similar shock wave above the cooling frequency, which is here, specific flux per unit frequency, has a dependence, first of all, no dependence on the density, and the dependence is only on the energy in the blast wave and the fraction of energy going into electrons. The dependence on magnetic field, which is captured here by the fraction of energy of the shock going into magnetic field, is P minus 2 over 4. With a P of 2.4, that dependence is magnetic field to the power 1/20th. So it's, for all practical purposes, there is no dependence on magnetic field, no dependence on the unknown density of the surrounding medium. So the beauty is that you can make a very firm prediction as to what the flux should be. 5 minutes. And let me just skip a couple of things here. So with that theorem, you have a very firm prediction of what the flux should be in the GeV. And that only depends on the energy in the explosion, the time at which you are observing, or Fermi lattice observing emission. So this is the expected flux for a sample of 5 bursts. They are not completely random. They are bright bursts for which we have good information, good data. But they are all cases for which we have good data, that Fermi has provided good data. So let's look at it. This is the expected flux. This is the observed flux. The uncertainty is primarily because we don't have a precise knowledge of the energy in the blast wave. And there is an uncertainty, maybe by a factor of about 2, probably not much larger than that. And you can see a very good agreement between the expected flux and the observed flux. Shui was saying that 2 magnitude is pretty good for theorists. This one here is not even 2 magnitude. It's better than a factor of 2. So look, the point being the following, that we have got a simple scenario which is very robust. It makes a very robust prediction, and the data, the observations made by Fermi LAT are not just consistent, they are in very good agreement with that theoretical expectation.
How did you decide at which time you take it down with the GeV emission? So you have...
It's a power law.
You have some...
It's a power law. It's a power law decay in time. So it doesn't matter. I could have taken any time. You could have taken...
This is the earliest time at which...
More or less. But it is after the prompt. It is after the... Correct. It is after the prompt phase, but then it doesn't matter. You can choose whatever time you wish. And there is a good agreement because the decay slope is also completely in agreement with the theoretical expectations, which, by the way, was the purpose of the slide that I just went over. This is showing that the slopes are in agreement. The temporal slope is totally in agreement. So now this is of the same thing. This is something that you have seen many people, that you can kind of not only look at the GeV, but you can look at the lower energy emission in the X-ray and the optical band, and they are totally in agreement. So you can do this exercise over 9 orders of magnitude in frequency space and several orders of magnitude in time domain. And there is a complete consistency between all of this thing. And so again, it could be a fluke, it could be a coincidence, or there is something real to it. And this is just showing you that there is something real, that you can take the predictions and observations of the Fermi LAT and then use that to make a prediction as to what you should see at later time in the optical band and the X-ray band. This is the expectation based on the Fermi LAT data, and then compare it with the actual observations. And you see a good agreement between the two. You can run this movie backward in time by pretending that Fermi doesn't exist, and then only look at the optical and the X-ray, calculate the shock parameters from these, and run the movie backward and say, okay, what should, if Fermi were to exist, what's the flux that Fermi will see in the GeV? Well, the answer is, this is the expectation based on the optical and X-ray. And in cases where you have got this Fermi observation, you can compare. And you can see for yourself that there is a very good agreement between the expectation and what we see. So brief summary of this particular part of the talk is that, the flux between 100 MeV and GeV, as opposed to the flux in the MeV band, I think is understood. We do seem to understand where that is coming from. And at the risk of repeating is because there is a model which is very robust. It makes a very robust prediction of what the flux should be, which has very weak dependence or no dependence on uncertain parameters. And so you can be very confident about the prediction, and those predictions are in agreement with Fermi LAT. And so that's the story, that we understand that. So if there is an alternative story that you have got that says that no, the hundreds of MeV and the GeV are coming from some other mechanism, then you have to make a case which should be more robust than the case of this external shock that I have presented. It got to be more robust than that to be believable. And in that regard, I want to share, so there is a recent proposal by Beloborodov, who is not here, but he was there. I saw him in Sweden. So this is not something that I'm showing here that I have not told him already at great length. So there is a proposal. The idea is kind of neat idea, simple and neat idea, and that is the following, that GeV photons that we see are produced by inverse Compton scattering of electron-positron pairs, which in turn are produced by MeV photons scattered by the surrounding interstellar medium. That's the idea. That's the basic idea of Andrei. And he said that it is the right mechanism, and I would like to think that it's the right mechanism. I would love, because it's a very nice idea. But there are problems. The problems are of very serious kind, that for this mechanism, there is a firm prediction, and that is that the duration of the GeV pulse or the photon cannot exceed a few times the MeV time scale, or which means that it cannot exceed 3 times the duration in the MeV band. And here is a table showing what the duration is of the LAT emission compared with the MeV for the same 5 bars that I showed you. And they all exceed this limit by a large factor, by factors of 100 in one case. And so there is a big problem, but there are many other problems with this particular idea. And as I say, that this is not something that I'm just saying here, because it's much more constructive and useful to communicate it to the author of the idea. And I have pointed it out to him, and we'll see. Maybe they would be able to come up with a better idea to fix this thing. But it seems to me that there are serious drawbacks with this particular idea. To be fair and to be complete, Andrei says that, well, this particular mechanism of electron-positrons, inverse Compton scattering, for instance, would work for time scale, as I mentioned, 3 times the burst duration, but then afterwards, it is SSC process that takes over, so synchrotron in the external shock that takes over. And then you have got several different things that have to kind of match smoothly to give you a single power law. Is it possible? Of course, anything is possible. I mean, but I should really stop here. There's no point in going on, and I'm just going to leave the slide. This is not the last slide, but I will leave this slide to say that we do not understand everything about the GeV emission. There is a very nice puzzle. 10 seconds, I promise. We have seen a burst with photon of 95 GeV, and that is puzzling and troubling. And reasons are here, and I'm happy to now take questions. So.